All right, so welcome back. Today in this video, we're going to be looking at some more water resources and environmental engineering practice problems. In this specific video, we're going to be focusing on flood control. So this is part E of this section. And so let's go ahead and dive into some of the practice problems. All right. So number one says using the rational method, calculate the peak discharge for a catchment area of 100 acres, a rainfall intensity of 4 inches per hour, and a runoff coefficient of 0.6. Okay. So what information are we given? We're given catchment area. We are given the rainfall intensity. We are given the runoff coefficient. All right. And then we are asked to find peak. Whoa. It's not how you spell peak. Peak discharge. Right. And it should be using the rational method. Okay, so I don't know what the rational method is. See if I can rational method. I'm searching rational method in my FE handbook. All right, rational. Three things come up. Rational formula, rational method. Okay. Q, which is peak discharge. Okay, so that seems like what I'm trying to find, right? And then C is my runoff coefficient. I'm given that. Perfect. Do I have I? Rainfall intensity in inches per hour. I'm given the rainfall intensity in inches per hour. So I have that. And do I have A? Watershed catchment area in acres. So yes. All right. So I have everything that I need. So I know that I'm using Q is equal to CIA. C is equal to 0.6. I is equal to the rainfall intensity, which is 4 inches per hour. And then A is equal to 100 acres. ACR. Okay, so also it's important to note that if I have my area in acres, right, and I have my runoff coefficient, it's just a number, and then my rainfall intensity is in inches per hour, my peak discharge is going to come out in cubic feet per second. So just something to note. All right, so Q is equal to CIA. Q is equal to 0.6 times 4 inches per hour times 100 acres. And now I know my Q is equal to 240 cubic feet per second, or D. Number two, calculate the runoff coefficient for an area with an impervious surface of 50 acres, rainfall intensity of 3 inches per hour, and a flow of 120 cubic feet per second. All right, let's write out what we're given. We're given rainfall intensity, right? We're also given an area, all right? And then we're also given flow. Okay, and we're trying to find the runoff coefficient. Okay. All right. So how do we solve for the runoff coefficient? Well, I feel like I'm still in the right area. I'm given flow, all right? Q equals CIA. If I'm given flow, all right, which is my discharge of 120 cubic feet per second. I have Q. Do I have C? No, because C is what I'm solving for. Do I have I? Yes, 3 inches per hour. And do I have A? Yes, at 50 acres. All right, so we can write out our knowns, or the formula that we need, which is going to be Q is equal to CIA. Okay. Q in this case is known, and we know it's 120 feet cubed per second. We know that C is in question. We know that I is equal to 3 inches per hour. And we know that A is equal to 50 acres. All right. So when we solve, we get C is equal to Q over I times A, which is equal to 120 feet cubed divided by seconds. Okay. All over 3 inches per hour times 50 ACRES. That is equal to 0.8. Cool. 0.8. So B. So I know that my runoff coefficient is going to be 0.8 for this question. Let's look at number 3. So this one says, what is the primary purpose of detention basins in stormwater management and flood control? Okay. Let's take a look at it. So we're given detention basins. And we're trying to find the purpose. Formula is needed. Not applicable. This is kind of like a conceptual prior knowledge question. All right, so to increase the velocity of stormwater runoff. So what is a detention basin? A detention basin basically is able to keep and hold water, large amounts of water, but it also is able to control the flow. So like a detention basin, when you think of a detention basin, right? Say you got this road, right? My road, and guess what? I'm about to make this fancy. Probably can't even see the yellow little strips on the road, but I thought it looked cool. I'll just put my strips on there. Okay. All right, so I got my road, and water hits it, right? It's raining. It's raining. And so this water has to go somewhere, right? So I'm going to say that this is the lower point where our detention basin is. And so water is probably flowing into a catch basin. Right, and these are the little grates that you see. On the edge. All right, and so from there, you have these, so all the water's been taken from those grates. And so you got water flowing, right? This is where all the water's going. And then it's flowing downhill, right? So I drew that line kind of flat, but it's all flowing downhill into this basin, right? And the basin is normally the lowest point, but in this basin, this detention basin, there are, you might say that there's baffles, right? So the baffles are these little things that will slow the water down. Then you'll have grass in these that slows the water down even more. So it controls, it regulates. So if we're going through these answers, so to increase the velocity, you do not want to increase the velocity of water flying and busting through everything. So no. To permanently store storm water for future use, no, not necessarily. Because this is not like the clean water. It's not clean and filtered and all that. To regulate the rate of stormwater release and control peak flows, yes. So if you can set up, your baffles, your grass, all those different things to control how fast flow is going, then that's what your detention basin is supposed to be doing. And to accelerate the onset of downstream, you never want to accelerate water, typically. So no. All right, so answer is D. Cool. So hopefully that made sense. All right, so this concludes flood control for this portion of water resources and environmental engineering. The next video, we're going to be looking at stormwater and going through a few problems on that. So look forward to seeing you in the next video.